All right, I think it's time to start. So welcome to Questions to Make Your Storage Vendor Squirm. This talk is going to be focused on distributed storage systems. It'll have a lot of stuff that will be useful if you're buying, boxes from people, but it's focused on storage systems that tend to either let you buy your own hardware or to buy a selection of hardware from the vendor and say that they scale out so that you can add more throughput and more capacity and more IOPS by buying new storage and sticking it in there and dynamically allocating it. This talk is not about any particular storage system. It will draw from a variety of different systems, and it will be about questions you should ask to be an informed consumer to understand and classify your system. We'll talk about how your storage system behaves under stress and help you understand that. I don't think I'm going to tell you that any kind of storage system is bad. It's just storage systems have to make choices, and this will help you identify what those choices are and whether those choices are the choices you want to be making with the system that your application requires. And it will help you learn whether or not a feature is something you can rely on, or whether it's a feature that exists because a product manager went to a developer and said, hey, we need to be able to say that we support snapshots for this deal, and it doesn't matter if they work more than once. Because if you want snapshots in a storage system, it's important to understand whether or not you can actually use them, or whether turning them on requires breaking everything else. There we go. Okay, so my name is Greg. I have been working in distributed systems since my senior year of college at the end of 2008. I work, since I graduated, on a distributed storage system, which you probably have heard of and might have interest in being from OpenStack, but I promised I was going to try not to name anybody, so you'll just have to guess. And I work as a principal software engineer at Red Hat. So let's start off with performance basics in storage. An important question to understand is how much throughput you can actually get out of your storage system. A lot of times, a vendor will come up to you and say, hey, we've got this new hard drive or this new solid state drive that can do 500,000 IOPS and 1.5 gigabytes per second of throughput. And it's important to know what that actually means. And it's even more important in distributed storage systems because they can be so much more variable than just the one little board. As an example, a thing that drives me nuts as a developer, and I think probably drives every developer of any system, of any distributed storage system nuts, is we tend to get people who come up to us or who send emails to mailing lists that say, hey, I built this new awesome 3-node storage system. It's got, super fast NVMe hard drives, and each of those is NVMe storage drives, and it's supposed to be able to do 1 million IOPS on every drive, and I put your storage software on top, and I'm only getting 600 kilobytes per second out of it. And we go, well, okay, how are you getting that 600 kilobytes per second? What are you doing? And they say, oh, well, we're running databases, and so my vendor told me, a quick and easy one is just to run DD with DirectI on 4 kilobyte blocks. And so they don't understand sort of the limits of the system when you're doing that, if you're doing synchronous direct I/O. So when you do an operation, you have to send it over to the storage system. And so maybe it takes 1 millisecond to go across the network. And it takes 5 milliseconds for the storage system to write it down. And it takes 1 millisecond for the storage system to send back the answer. And so that one operation took 7 milliseconds to do. So if you're only doing one operation at a time, the best you're going to get is about 142 operations per second. And if they're 4 kilobytes each, you're getting less than 600 kilobytes a second. And sometimes this is the measure that you need for your storage system because it's really it's entirely synchronous and sequential. But real distributed storage systems are not built for this scenario. They're built for the scenario where you have one client sending a bunch of I/O and then a whole bunch of other clients also sending a bunch of I/O to the storage system, so that you can simultaneously have lots and lots of those operations in flight. And each one of them might take 7 milliseconds, but you've got hundreds or thousands or tens of thousands of them going on. And so overall, they add up to very large storage numbers. But there is another tricky bit here, which is that sometimes that one I/O might take 7 milliseconds to operate. But if you've got 100 I/Os, then they each take 9 milliseconds. And if you've got 1,000 I/Os, then they each take 20 milliseconds. And if you've got 10,000 I/Os, then the system can't actually handle that many, so it just falls over. So it's important to understand both what your storage system, or what your application needs out of its storage system, and then how the storage system will respond to those I/O patterns. Secondly, if you're building a distributed software-defined storage system, it's important to realize how many disk I/Os on your backing hardware are going to happen for every external I/O. You might come in and say, hey, like, I've got a storage system, it's 10 hard drives, they can use to 100 ops per second, why aren't I getting 1,000 IOPS? The answer is, well, it's a distributed storage system with replication for failure recovery, so the very best you're going to get if it's 3x replication is 333 IOPS. But many storage systems don't even do that well because maybe they have to do journaling or extra metadata updates for every I/O. So you might only get half that or some other completely different number. It depends a lot on exactly what the storage system is doing. So you need to get details from the vendor and then run tests in your configuration to see exactly what you're actually going to get. Related to that is the caching behavior of the storage system. Caching is sort of a fundamental way that storage vendors and systems like to tell small lies to you in order to give you much better performance. This started with hard drives. They put in a little bit of memory in the hard drive so that when you send it to write, you can say, OK, I'm done right away, and then sort of write it out to a persistent storage later on when it's convenient or whenever you tell them to do an fsync. So it might be that you've got some library that you're using to write to the storage system, and maybe the library it has its own caching layer and is merging IOs for you. Or it could be that if you send off an I/O to a storage server from the library, then the storage server responds right away when the data is in memory, and then it just goes out to disk sometime later, and maybe you can send specific operations to make it flesh it out now, or maybe you can't. A good way to help identify this specifically is to ask about direct I/O. Let's say you can say, hey, I've got two clients that are doing direct I/O to the same block device or the same object. And if I submit a direct I/O write from client foo and it returns complete, and I do a direct I/O read from client bar, am I actually going to see that data right away? Or is it doing caching in some layer that won't tell me? And I know storage systems that behave in both ways, and sometimes you want one or the other. Just because it doesn't do direct I/O out to the server doesn't mean it's not safe. It might be that like the client has its local cache and it respects fsyncs and stuff correctly, but it wants to cache locally so that it can merge IOs, and you can do like 10 IOs that all get merged into one operation against the backing cluster. All right, so data safety. There's this thing called the CAP theorem. Storage engineers and academics get in huge fights over it and over exactly how much you should care about it. But I'm on the side that says you should care about it a lot. In any storage system, you're going to have nodes fail or network partitions. So that means, and when that happens, your storage system needs to decide. Is it going to be very consistent about the data it gives you, or is it going to let you access the data no matter what happens? So in this example here, we got 3 storage boxes, and one of them failed a while ago. So maybe it's rebooting, or maybe it's actually dead. But in this case, let's say it's rebooting. And so we've written more data to the second storage boxes. And this is like a 3 replica system. So it's a shared piece of data that they all have. So we've extended it. And then, oh no, all of the storage systems are down now because these two, actually, there was a power surge and they died. But we got the first one back. And so at this point, the system needs to decide, hey, I don't have the newest piece of data. I'm missing some of it. Am I going to give you back the old data, or am I going to keep telling you, no, this data is not here right now? In some scenarios, you want it to give you the data right away. If you are Amazon and I have put 7 items in my shopping cart and then I'm going to my shopping cart to check out and you can't find it, Amazon would much rather give me 6 items that I can buy right now than say, oh, sorry, it died. If this is a block device, maybe running a database or like financial transactions, you probably don't want to go back in time without knowing about it. Related to that, but separate, is the minimum number of failures to lose a write. You might look at a system and it says, hey, I'm a 3 replica system. Everything is replicated 3 times, and say, OK, so I'm not going to lose any write unless I lose 3 nodes after that write happens. But that's not necessarily true. It could be that you're writing to a chunk of a block device or to some object that has 3 copies, but 2 of them are down. And at that point, either the system needs to let you write to the 3rd copy or else refuse the write. And if it lets you write to that 3rd copy, then it only lives in one place right now. And so if you lose that, then you have no copies of that write. And so if that third copy, which has the newest data, is gone, then you can get back all the old data and have 2 copies of the old data available, but none of the new write. And so even if you have an available system, you might not want to have it quite that loosely available, or that loosely consistent with your data. And if you have a consistent system and you only end up writing 1 write on a 3 replica system, and then you lose that one, you're going to be very unhappy because the system is going to say, hey, like, I lost the newest data, I can't get it back, I'm going to deny you all I/O until some administrator intervention happens, which is probably to say, hey, yep, that disk is gone, we're going to roll back in time, but in the meantime, it took me 20 minutes to respond to the page. Similarly, the way data failures are partitioned is very important. It could be that in this case, so we're going to pretend that each of these is actually some kind of replica set or whatever, that you have, you know, these 3 nodes or 3 nodes in the system, and one of them died, and so that whole set of data is unavailable. In this case, the blue data is unavailable, but this was just one customer. So now we have one very unhappy customer because all their data is gone, but all the other customers didn't notice anything. Another option for a storage system is to sort of stripe the data widely, where every customer or every block device or whatever lives on every single storage node. And so now everyone's lost 1/3 of their data. Now it could be that that 1/3 of their data is, you know, backups running off of their home PCs that they only care about when they're trying to restore from backup. In which case, you know, probably you've actually got a long window before anyone cares. Or it could be that this is their block device, and now 1/3 of everyone's blocks on their virtual hard drives are reporting I/O errors, and no one can do anything. And that combines really terrifyingly with available systems, that sharding. So in this case, let's say we've got, you know, we sort of had 3 pieces of data. One of them was a database index, one of them was the database data part 1, and one of them was the database data part 2. And we lost one of the copies of the database data part 2, and we have a stale copy. So if we have an available system, and then the storage system is going to start serving up that data from the old one because it doesn't have the new one, it wants to tell you about it, but it's not consistent with the index. So what are you going to do? All right. How fast does recovery actually happen in your storage system? In this scenario, you know, we've got a bunch of stripe data chunked all over the system, and we've lost 1 node. So we have a choice to make. We could devote all the I/O in the system to recovering and re-replicating everything back to 2 copies of data. But then clients can't do any I/O because we're devoting it all to recovering as quickly as possible so we're as safe as possible. Or maybe we only recover when the clients aren't doing anything, but clients are really busy on this cluster, so it's going to be 3 months, and we really hope we don't lose another hard drive. Every storage system has to make this choice. Usually it'll be configurable in some way. They might or might not let you configure it. And the ways they do that range from very complicated to looking very simple and being very complicated in the back end, and they hope it works out. So understanding with your storage vendor what they prioritize, what they let you control in their prioritization, and how hard it is very important, because you might say, okay, no, like, I need all of my clients to keep functioning all the time. That is more important than that I have exactly the number of configured copies. Or it might be that you need exactly the number of configured copies, and if everyone has to take a hike for an hour while that failure recovery happens, too bad. But there's another thing you've got to think about in this case that a lot of people don't plan for, which is that if you lose 1/4 of your nodes, you've also lost 1/4 of your bandwidth and 1/4 of your IOPS. So you need to over-provision your storage system by enough that it can both do recovery and continue serving the client I/O load after whatever number of failures you want to provision for. Because otherwise, you've lost 1/4 of your IOPS, your clients are continuing to write at 95% of the capacity of the old system, and every I/O just keeps on taking longer and longer and longer, and eventually you get these timeouts, and storage and your OS starts throwing errors and saying, hey, my block device is completely unavailable, what are you doing? And everything grinds to a halt. Another interesting question is how you can back up your data. People used to ask me this when I'd only been working in the field for a couple of years, and I was just like, you're kidding, right? Like, this is 3 petabytes of data. How are you going to back it up? But people want to, because they want to not be subject to one software point of failure, or because they really do have fast enough interconnects between data centers that they could transfer it across the network or whatever. So there's sort of a fundamental trade-off between, when you're doing backups, between how new your offsite backup is and how much bandwidth is required. Sort of the very best thing you can imagine is, oh, hey, my offsite backup is always perfect because we only do synchronous I/O, and so we wait for it to be replicated off to the offsite backup before we return to clients. But then you need, full bisection bandwidth across your networks, and no one can afford that. So, your backups might be crash consistent, which is really nice, but means that you probably have means that you're probably requiring a whole lot of network bandwidth. It could be that they're eventually consistent where, if you don't do any writes on the system, on your primary system for a long enough time, then the replica system will end up looking that way, but it won't take the same path. Or it could be that, it copies, the current version of every piece of data when it runs through. And so you need to understand how that works. So that brings us to the cost of enabling features in your storage system. I think I'm talking faster than I was earlier. Many features impose some amount of overhead I/O when you turn them on. The coolest ones often require work on every I/O once you turn them on. And sometimes that work is being done by the system whether you're using the feature or not. And sometimes once you turn on the feature, then your performance drops by 30%. And so it's important when discussing features to find out how those costs work. For instance, one good one is snapshots that will illustrate this nicely. You sort of have several choices when doing snapshots about where you pay the cost, but you do have to pay a cost because you want a copy of the data. So it could be that you take a snapshot of a block device and just every storage node in the system says, all right, we had this block device, which is these red blocks, we wanted a snapshot of it, so we copied them and now this blue stuff is our snapshot. And that's a one-time cost. It's really easy to understand, but it also means that creating the snapshot requires I/O linear in the size of the block device, and you have to wait for it when you do the snapshot create command. Or it could be that you overwrite to new locations, so your snapshot is actually the existing red data, and as you add new data, then it's this blue layer. And so you pay the cost as you go, but you probably have to pay a little extra cost to maintain the metadata about whether you're looking at the blue or the red objects. So there's a little extra I/O involved. Or it could be that you say, okay, no, I don't want to do the extra I/O to do the metadata, but what I'm going to do is whenever I touch a block, I'm going to copy that whole block or that whole chunk of the block device into a new location which I know to reference. But then you're sort of expanding every I/O. So you might be doing a 4 kilobyte I/O that requires doing a 4 megabyte read and copy. There are lots of other solutions, but those are sort of the basic families to choose from. And you'll notice that each of them has very different sorts of costs. So our initial copy one, you had to copy the whole block device, which requires the bandwidth, and so sort of the time and also the extra disk space. The overwrite to a new location required no extra bandwidth as you're doing it and just sort of incrementally, but required extra I/O to maintain the metadata. And then when you do the block copy, then you didn't have to do extra. Then you had to do sort of a read and copy on every access to a new block in the system, which depending on your pattern might be very cheap, or it could be that you're doing random 4 kilobyte I/Os and there's 1,000 object chunks in the system, and so your next 1,000 random I/Os are suddenly paying a 4 megabyte cost instead of a 4 kilobyte cost. And depending on your application, one of these might be unacceptable. They might all be acceptable. It's important to know. Going back to the backup system, there's sort of a terrible irony that your backup system is going to impose extra load on your primary cluster in order to keep it safe. Either you need to do more writes to tell the replication or you need to do more writes to say, okay, like these are the changed pieces of data that you need to go look up and copy, or else you need to do reads of all the data in the system to find out which ones have changed since the last time you did it. And if you got an active-active thing, then you need both of your sites to handle the load of the whole system, even though, from the client's point of view, they're split. There are several I've got several examples here that cover the spectrum. I want to be clear that most of the time when you're doing backup, you know something about the workload, so you can do better than these. But this is sort of the basic choices you make, and then you have to figure out the hacks that let you be better than this. The first one that we're going to talk about is full data journaling. It could be that you've got sort of your data layout, and you're just like, you know what? I'm going to, every time I do a write to that data, I'm going to stick it into a journal off to the side, and I'm going to have a daemon running that copies that journal over to the backup site and applies it to the local objects and block devices there. That's nice because it means that you can sort of offload the work, the cost to your nodes that are responsible for maintaining the journal in the backup system. And it's really easy to get crash consistency out of the system because you just replay the journals, in step to make sure that if you have to do a failover, then hey, I have every write in order. It's easy to make sure it's easy to look like we just crashed and restarted. The problem is that you're doing every write twice. That's extreme disk overhead. It's network overhead. And that the network, and when you do this, the network interconnect between your data centers must match the write throughput of whatever systems you're replicating over the network. Man, this is not doing great for me here, is it? Okay. Another thing you could do is instead of copying all the data, you can say, oh hey, I updated this object, this S3 object, or I updated this chunk in my virtual block device. And so you maintain just a little log that says which pieces have been updated, and then you copy those pieces over the network at some, either via polling or push model or something. That's nice because it's a low throughput overhead on the writer side, and you don't need very much bandwidth in the disk or the network, and it's easy to trade off how recent the backup is versus the interconnect bandwidth, because if you've got a 10 megabit connection, then you probably are doing more than 10 megabytes of updates continuously in your data center, but it might be that you're overwriting data so much that you can replicate all the objects which change within a day over that pipe. The problem is that it's hard to keep consistent across the objects and blocks on the backup device because you're just sort of oh hey, this object changed and I'm reading the newest version of it. And so if you had 3 objects and one of them changed once, and then the second one changed, and the third one changed, and then the first one changed again, you're just going to see the final state of all of them without any of the intermediate states. And then another thing you can do is that you just don't do anything extra to help the backup system out. And whenever you want to do a backup, you crawl every piece of data in the system, and you say, hey, are you newer than the last time I copied you? And if it is, then you send that over the wire. That's nice because there's no write overhead, and it's really easy to implement. It's bad because you have to read all the metadata in your storage system, and it's basically impossible to keep it consistent. This has been done before. It was really interesting to watch a company say, hey, we loved this geo-replication feature. It was everything got copied in seconds when we were testing it, but now we've got 1,000 customers with a couple million objects each, and we're 7 days behind and falling farther back all the time, even though the churn is very low. And it was because it had to read those millions and millions of objects on the active site and find out which of them mattered. That system does not work that way anymore. I think I've been talking fast. Okay, so those are some specific examples of features, but you can do this generically. Basically, everything takes I/O, and so when you get told about a cool new feature, you've got to remember to ask the vendor, hey, what is the I/O cost of this? When do I pay it? Does it happen when I take a snapshot? Does it happen on every write after I do the snapshot? Does it happen when I delete the snapshot? And you can sort of apply that framework to any feature in a storage system. And I can ramble on for a while, but when I practiced this took longer, so I'm out of slides. So I guess we'll start with questions, and otherwise I can tell you about how people lie in performance benchmarking. Okay, performance benchmarking it is. Yes?
Have you seen any situations where there's kind of like a combination of those different approaches to backup? Like we're maintaining a journal, but there's also metadata associated with the block, and we can make a trade-off.
Almost always there will be some combination of it at different levels of the storage system. You might say, hey, like, you might sort of at the high level have a daemon that's running that like runs through all the virtual block devices to find out which ones need to be changed, and it might just pull each of those, and then each like block device might maintain sort of a map of changed objects in the timestamps. It might be that, yeah, there are some storage systems where everything is actually log-based, and they're called log-structured file systems or log-structured systems. And so actually like doing the log-structured replication is really easy there because you've already got it. You just have to like not trim it and clean it up until later on. Okay, so storage benchmarking is a huge lie all around the world. I think, let's see. You can sort of use it to see what's possible with the storage system, but you have to ask them the questions about exactly how they tested and what they were doing. If you see a fancy number like, oh, hey, we put together this really fast SSD system and we got 1 million IOPS out of 3 nodes, like, that's great. But ask them what the average latency was on each of those operations. Ask them, you know, what kind of CPU they needed for them. Because it could be that the average latency was actually 20 seconds. And I mean, that's a great number, and maybe your application really can handle a 20-second latency, but your operating system on a virtual block device, it cannot. One of my favorites is when people put out competitive benchmarks between 2 storage systems. I'm going to call one water and one ice, and I hope that's not a real storage system. So let's say that you have this vendor releases a benchmark that says, hey, we put together a 3-node storage system and we ran both water and ice on it. And on the water storage system, we got 1 million IOPS, and I don't even know what the right number is, 10 gigabytes per second of throughput. And on the ice storage system, we got 1,000 IOPS. Oh my God, water is so much faster than ice. But then you go look at what happened, and it turns out that these 3 nodes they used were reference architectures for the water storage system. And each one of them had, you know, 1 NVMe SSD in it and 10 hard drives. And so they said, hey, it was like a storage system sized for 10 hard drives replicated 3 times. And oh, the ice system doesn't actually use the NVMe SSD, but the water system uses it for caching every write. And the amount of data they put into the system fit inside of the NVMe SSD and never overflowed. So what's actually happening is that you're benchmarking the I/O you can do against an NVMe SSD against the I/O you can do on 10 hard drives. And I have seen benchmarks like that, and they do their very best to obfuscate that that's happened because they're like, oh, we set them up according to the recommended settings on this hardware. So beware of competitive benchmarking. I mentioned those latency curves earlier in the talk about how long every individual I/O takes with a certain parallelism. That's important to talk about when you're looking at your system. Okay, I'm actually out of stories that I had prepared now. So I think we got about 10 minutes left. I will stand here and take any questions if you want to raise your hands. Otherwise, enjoy the conference. Thanks, guys.